Hello and welcome. Here we are in Lecture 13. This is a special encore presentation because unfortunately the recording from yesterday did not work out. Fortunately, I do have the chat transcript from yesterday's lecture, so I'll be able to repeat many of the questions that were asked to try to make this as interactive as possible. So as you can see from the title, today's topic is a case study. It'll be fun. So we've been learning a lot in the last few weeks about various features in Chisel, some features in Scala, more general hardware design concepts. And today we're going to put it together to really demonstrate this agile hardware design process at work, right? So we're going to iteratively take a design and make it better and slowly keep tweaking it. In particular, we're going to start from a queue, and we're going to keep making our queue better and better. And when you look at something like the queue in a standard library of Chisel, you might say, oh wow, that's very impressive. How do they write that? And the answer is not all at once, right? You need to start simple, close the loop early, and then keep finding ways to improve it. That's what today's lecture is going to be about. We're going to keep talking through code, ways we're going to deliberately aim for less ambitious targets and make it more accomplishable, accomplish those goals, and then improve and iterate from there. So let's go. So as I said, we're really going to be designing this kind of iterative agile approach, and as part of it, we're also going to be thinking about how to make things more reusable. Let's go ahead and load up our notebook. Okay, so a large part of motivation for the things we cover in this course is trying to improve hardware developer productivity. And part of how we're trying to accomplish that is through reuse, right? Rather than having to write every piece of your hardware over every time you use it, try to be able to reuse parts to reduce the portion you need to develop. In particular, reduce the portion you develop to the portion that is unique to your design. And things that are common or used elsewhere, hopefully you can reuse, right? And so that reuse means reuse some sort of similarity. In particular, means some sort of pattern, right? Where I need a hardware that does something that kind of does something like this, right? And so recognizing that pattern, that common trait, that common behavior, that's kind of key thing to making a reusable component, right? And so we're going to use generators, of course, to make it parameterized and nice, but the key thing is recognize the pattern, right? And so, for example, today, our pattern is going to be about a queue. Now, we're trying to do this, iterative, agile, progressive design process. Really what we're trying to do is we're going to kind of go slow and steady, right? So rather than trying to take these giant leaps, we're going to figure out how to make very small, manageable technical steps at a time, and we're going to go through it, right? If you think about many experiences you've had developing, whether it be for hardware or software, pretty rarely are you limited by how fast you can type, right? Usually you're thinking about what needs to go next, or more commonly debugging, right? And so that's kind of the mentality we're going to take today. We're going to figure out how can we go about reducing debugging time. Reducing time, you need to think about really hard, complicated things. And as a result, we're going to improve the overall productivity, right? And so we're going to do that by taking smaller steps at a time. And so really kind of the goal is to think about what is the simplest thing I can get going, and then figure out the other features you want. Just because you don't do them the first time doesn't mean you're never going to do these features. It just means they aren't part of your first version. And you can figure out a way in a roadmap where you can add these features on. And rather than building all these features in isolation and then trying to integrate them all at the last second, we're going to continuously add these features on to a working system, right? We're going to go from working system to working system. And so really the goal should be to kind of, we keep talking about closing the loop, right? Get something where you have a design, a test, and you're able to run it, perhaps even get the physical design involved and see how much it costs, and get that understanding early on, right? And so we're kind of looking at design. We should be looking for what functionality can we defer to a later version, and for optimizations, what optimizations can we defer to a later version, right? And so really kind of think about what's the simplest thing, and also what would make it easier and more tractable to test, right? And these other features, optimizations, they will happen. We just need to figure out in what order, right? We can kind of do a cost-benefit analysis and think about, how much improvement would that functionality give us? What might it cost? And, perhaps schedule it intelligently, right? Maybe this functionality can be easily built other functionality before it, right? And so maybe I'll choose when I schedule that. And so you kind of get this roadmap where, you have your most simplest thing, you close the loop, it's your minimum viable design, and then you're going to kind of keep adding things onto it to get to the point where you want to have something that has all these features and is well optimized. And, it's okay along the way if you change your and revise your roadmap. That's kind of important, right? The whole point is to have a kind of simple thing and then progressively, iteratively go on to it. So today, we're actually going to have this little microcosm where we're going to show a queue And we're going to go through this process and actually go through multiple versions and keep showing how, well, this functionality we can defer, but we're going to fix this other thing first, right? And kind of show this not only conceptually, but also with actual chisel code. So as I said, we're going to talk about a queue today, and we're going to make it behave just like the queue you see in the chisel standard library. So as a reminder, right, the queue is this device where, it's a FIFO, things come in, things come out. Both interfaces are decoupled, right? So they have that ready valid signaling protocol. And you can know NQ on one side and DQ on the other. And so in particular, we want a queue that's parameterized both on the data type it's enqueuing, as well as how many elements it can hold, right? And so that's going to be our goal. Additionally, we would like to have it be efficient in terms of the hardware design. So one term you may not have heard me say much this quarter is PPA, which is short for Power Performance Area. These are kind of the common concerns within the hardware design community for how well a piece of hardware functions, right? Where, in software, maybe mostly they're concerned about how fast is it. At least in the modern era, perhaps, historically, code size is a bigger problem, but, nowadays, execution time is probably your biggest concern. Maybe memory capacity when it's in use. For hardware, our metrics are, okay, how fast is it performance? How much power does it take? Because that's really going to matter when it's operating, and then also the cost or area, which is a proxy for manufacturing cost, right? And so if you make our hardware smaller and simpler and cheaper, that's going to be great. And of course, if we can make that also solve the problem faster, it's also great, right? So today we are going to be talking a little bit, kind of in very indirect terms, about how can we make the hardware more efficient and consider some of its concerns, right? And so I said, for us, our whole plan is to get closed loop as early as we can, so we need to think about what's the simplest thing we can do, right? We want to, defer a lot of the complexity until later on. We'll kind of work our way there. And so, in particular, what we're going to do is we're going to strain ourselves initially, and so these are deferring these functionalities. Not that we're not going to do them, we're just deferring it, both in terms of parameters and performance, right? So for parameters, instead of being fully parameterized, maybe we'll say, you know what, you're stuck doing a one entry queue at first. And for data type, we're going to say uint for now, for example. And what about performance? Well, you know what? As long as you do the right thing, but it's a little slow, we're going to be okay with that. And we're going to figure out ways to make it go faster. Okay, so yeah, our first attempt at a queue, and this is the minimum viable thing. Well, it's going to have one entry. And we're going to, still support the decoupled interface. If we really wanted to go more minimal, maybe we wouldn't even have the decoupled interface, but let's keep the interface the same. So we'll have a decoupled interface. So we still have, the actual payload, the dot bits, the ready valid. Our queue is going to be just a single entry. And that's going to hold like the bits, the data. So we're going to use a register to hold that. We're also going to need to have some metadata to kind of know how we're doing. And well, for now, we're actually just going to use a single bit to track whether this register has data in it or not. And somehow, based on these two registers, we need to kind of connect some logic to do that ready valid protocol, right? Now, in terms of the corner cases here, remember the chisel library implementation of the queue has these additional parameters, pipe and flow. Pipe, if true, means that if the queue is full, which normally would mean you could not enqueue because it's full, you actually can enqueue if at that same time you're also dequeuing, right? Because as you're putting something in, something else coming out. So pipe, of course, is short for pipelined, and that's kind of implication. So actually, for today, that's going to be our goal. At times, we're actually going to have to give that up, but we'll eventually try to aspire to return that functionality. The flow functionality is if the queue is empty, an entry can completely bypass the queue and spend 0 cycles in the queue. We're not going to target that at all today, but that's the feature available inside the chisel standard library queue. But yes, so our goal is, of course, to build a single entry queue. We're going to support this decoupled interface on both sides, have a register to hold the data, and have a single bit to kind of track the status or the metadata in a way. Okay, so how are we going to do this? Well, we need an I/O. So we're going to have a decoupled input. It's flipped because decoupled by default is kind of in the output direction, then our DQ for the output. Because it's really easy and doesn't really require any kind of complexity. Really, we're going to parameterize the bit width because that really doesn't cost us much. There's no reason to be extra obtuse when we don't have to. We can be a little bit pragmatic here. So yeah, it's a parameterize in terms of width of uint, but it's still a uint. We'll wish it would be something else eventually. Okay, so what's our V0 going to be? Well, we're going to have this I/O. I took the time to put this bundle in a separate class, so that way in future invocations I can just only use one line to kind of save screen real estate. But okay, we have a register for our actual queue entry. We have a register for our metadata. We talked about a single bit. And then how do we wire it up? Well, as you saw from the prior slide, we're going to go ahead, and wire up the register to the input. And then how we're using it? Well, we're going to use that single bit to track if we're full or not. So in particular, when are we able to accept data? Well, if we are not full, meaning we are empty, right? Or if we're dequeuing, right? That's kind of when we can take data, right? So kind of we're just talking about a second about that pipe feature, right? So this is that pipe feature in action. If we're dequeuing, we're able to enqueue because there's a space being opened up by that dequeue. Otherwise, the only way we can enqueue is if we're empty, i.e. not full. So this bit's going to be 1 if there's an entry that we care about and 0 otherwise. So do we have anything to dequeue? Is that dot valid for the dequeue side? Well, if we're full, we do. Otherwise, we do not, right? And of course, our dequeue bits come straight from register. No reason to put any conditionality to that. And then we have these two cases, right? If we're dequeuing, we're going to go ahead and mark ourselves as empty. Meanwhile, if we are enqueuing, so remember the dot fire is this nice functionality that this captures when ready and valid is true on that particular port. If we're enqueuing, well, then we should, of course, make the entry those bits that are coming in and mark ourselves as true. And so one thing I want to point out is that today, sometimes the way we write this code is going to look a little bit more like software code, a little bit less like hardware you've seen so far, right? This is very much valid chisel. We're going to see chisel very much like this the rest of today, but unlike we've seen before, the order of the lines doesn't start mattering more, right? Where, for example, these lines could be completely reordered without any consequence, right? Because they're simply just describing connections, right? This is connected to that. This is connected to that. Now, with the when statements, now the order potentially starts to matter a little bit more because a few things, right? Number one, the when means the condition is conditional, right? So even if it's connection to CIDR, connecting this full bit to false, that's only going to happen if this condition is true, right? So number one is conditional. And number two, as you can see, we also have multiple assignment, right? So if we have multiple assignment, assigning the same thing or connecting the same thing multiple times, let's just say, last connect semantics, right? The last connection is going to win. And so, if we're going to assign full and potentially in 2 locations, we need to make sure, which order takes precedence, right? And so in the case of this pipeline scenario, this is going to be great where we're going to, if we're enqueuing and dequeuing at the same time, well, the dequeue is going to set to false, but the enqueue is going to set to true, right? And so we actually do want it to come out at exchange being true, right? Because there is an entry in there. The enqueue did succeed. And of course, when you imagine how it's going to look, the bits itself going to go, if it was 1, even with a simultaneous Nq DQ, it's going to still be 1. It's just the way that the tool flow is going to prioritize and order those muxes in the generated hardware. It's going to give this Nq set of muxes the precedence, right? But cool. So we have our mux. This is our simple little thing. It's 1 entry. We can go ahead and build this module. To test it, this is the a variation of the code we saw earlier in our arbitration lecture, testing lecture for how to test the queue. We have this Scala model using this collection, and we need to be a little bit clever about how we use things like ready and valid to kind of make sure the right timing behavior, right? Where in hardware, a lot of things happen in parallel because it's kind of the natural behavior of hardware. With these models where now we're executing in an imperative program, we need to make sure we evaluate those in order to make sense. In particular, one thing that's a kind of good model is when it comes to state elements, it's good to read them and then write them. However, in the case of this queue, to get the Nq DQ behavior to kind of match the simultaneity we had before, we actually want to do the DQ before the Nq to make room for that new element, right? Okay, let's go ahead and build that as well and keep going. Okay, so if we want to go ahead and simulate a cycle, this is code very similar to what you saw previously. You're actually going to see me repeating this code throughout today, and I'm going to be, basically mostly repeating it in order to specialize at the current queue. Most of the by is not going to change. I may able to do some subtle changes around here to kind of accommodate how certain queues might have slightly different timing behavior. but it's not too crazy, right? For example, in this case, what we're going to do is we're going to look at and see, does the queue mark itself as having something valid to the queue and isn't, not empty, and make sure the model agrees that should be the case, and then, look at what's there, right? We're also, of course, going to connect the model multiple ways and compare it all. Cool. So we covered a lot of some testing lecture. This is very much similar to the code from that lecture. If we go ahead and run it, we can see the queue is going to, NQ and DQ just fine. Cool. So let's take score on how we did so far. We implement the queuing behavior, right? We're able to kind of NQ things. It's only a single entry queue, right? So we put 1 in there. We tried to put 2 in there, but we weren't ready to DQ, so it couldn't get in, right? But then we are ready to DQ, so 2 comes off, and then we keep going. We parameterize data width, which is nice, but it's still a uint, right? So what are our major shortcomings so far? Well, really, it's just the fact it's a single entry, right? We were hoping to have a parameterized queue depth, and right now we basically made a single flop, right? A single register. Okay, so we're gonna need to try and go ahead about fixing that. Okay, so if we want to parameterize some registers, how might we do it? Well, the first attempt might be, what if we used a shift register, right? I remember from earlier in lectures in this course, we've kind of given different names to the exact same piece of hardware. You can call it a shift register. We call it a delay N. In the Chisel standard library, it's actually close to something called a pipe. But you can see the functionality, right? We have a bunch of registers in sequence, and the output of one feeds into the input of another, right? And so yeah, we can connect the input of our queue to one end, the output to the other end. How would this work? Well, we would need, a register for each element, okay. And we'd also want a little bit of state to kind of track, is that element full or not? Okay, that seems doable. We know how to build one of these with, either recursion, functional programming, or for loop. We've done all 3. We can kind of build that topology. And somehow we need some sort of cleverness to actually do the protocol for over here, the logic kind of connectivity. So let's try this out. So here we go. Here's our next improvement. And so what we're going to do is we're going to have some number of entries, as well as, we're going to use, in this case, a Scala collection, right? So let's talk about why we did that. We're using a Scala collection, a seek in this case, to hold our registers because we don't need to dynamically address these registers when the hardware actually exists, right? We need to hang on these registers within this generator, within the Scala program, as we're, manipulating them and connecting them. However, once the topology is set up, as you can see in the prior slide, we don't need to dynamically address them, right? We're always coming in here, always going out there. These connections are all static and predetermined. So we don't need to have that connectivity. That flexibility. So a Scala collection is the perfect thing to use here. That's why we're using a seek, and we declare it for both the entries as well as the full bits. Now you may notice for the entries, we just declare as a register. For the full bits, we actually bother to give them initial value of false. And that's we want to make sure they're initialized to 0, right? Because when this thing turns on, we want to make sure it knows it's empty, right? Otherwise, it could be garbage state. We don't know what it is. And we have this convention where if an entry is marked empty, we actually don't care about the contents of that corresponding queue entry, right? We're not going to look there. We're only look there if it's full. Okay, so we have our n registers and our n bits to track if they're full or empty. In terms of the order, we're going to decide to NQ at the end and DQ from the front, right? So, index num entries -1 is where we're NQing, dot last in Chisel terms, or Scala terms, and we're going to DQ from index 0, i.e. dot head. The reason why this choice was made will be more apparent when we see some of the later designs. But in some ways, it's pretty arbitrary at this point. Okay, and so what are we going to do? Well, we're going to need a few things. We're going to need to recognize when it's time to shift, right? So by shift, of course, that means everyone's going to take the value of their input and make that their value, right? So at the same time, they're all going to read the value from above, and it's all going to kind of shift the data down. Okay, so when should we do that? Well, if we're DQing, yeah, we should move everything down, right? There's somebody at the tail, we should get that out of there. The other time we should shift is actually if that last entry is empty, right? That one's a little more subtle, right? So why should we shift if it's empty, right? If it's empty, wouldn't that mean that all of these are potentially empty? And the answer is no. And you can already kind of see one of the shortcomings of this approach is that if someone NQs sporadically, NQ, a couple cycles of idleness, NQ, you actually will have bubbles in this queue, right? And so it's important we kind of squish those bubbles out. So if you see it marked as empty here, you actually want to keep shifting down to squish out that bubble because there might be actually a valid entry behind it. Okay, so yeah, we're going to kind of keep shifting down anyways because there might be bubbles. We'll come back to this bubbles issue in a second. Okay, and then, well, what about NQing? Well, we're ready to NQ if the last entry is available, right? I.e. it's not full. Remember last, of course, is the place where we directly NQ into. Or if we're shifting down. Remember that pipe feature, that pipeline feature where we can, NQ for dequeuing to a full thing if it's for dequeuing? Sorry, NQ into a full queue if we're also dequeuing at the same time, right? And so that's that in action. Great. Of course, is there anything to actually dequeue? Well, only if the last thing is full. Otherwise, we should be careful. And what are we dequeuing from? We're dequeuing from head, index 0. Okay, so let's look at how our code works. So for shifting, we actually opted to go with the for loop here. And you can kind of see the connectivity pattern where, because this is inside a when block, right, these registers are going to otherwise hold their value. And only, when condition shift down is true, are they going to be connected to their predecessor in the queue order, right? So because we're shifting down, that's, going from index I to index I minus 1, that's why you kind of see this connectivity right here. And of course, we also are shifting in an empty spot into the last entry because we just shifted down, right? So now there's a free spot at the end. However, when we're NQing, and remember shift down is triggered by dq.fire. When we're NQing, we are going to, of course, take that last entry and put it in there as well as mark it as full, right? And remember, nq.fire is only possible when io.nq.ready is true and io.nq.valid is true. And so we control .ready, and so of course that's required as room, right? So, okay, so cool. And just like the prior one, right, to get that pipeline behavior, we're going to do kind of the dequeue first and potentially enqueue and override it second. And even though I say first and second, this is actually, think of more as precedence, where we're giving the enqueue greater precedence. They're happening in the same cycle, right? You're never going to see that value glitch to 0 or something. Cool. So here's the entire design written out. We did it with whens and for loops here. We just did a 3-lecture sequence on functional programming. So code reduces functional programming. Yes, and it's extremely concise. I do have hesitations about its readability though, which is why I commented it out. So let's look at what we did here. So we have 2 when blocks, a for loop. All of this somehow turns into just 1 when and 2 lines. Yeah, let's talk through this, right? So for the shifting, we're doing that with a fold right. So we're using the fold that iterates through the elements, and we're passing along a connection to the last entry we just did with, and that's how we're using that to kind of iterate through it. We're doing fold right because we want to decrease an index, right? So remember, we were kind of shifting down, going from high to low. That's why we're using fold right rather than fold left, for example. Okay, so this is going to start at a maximum element index and work its way down. And our function literal, what does it do? Well, given the element is presented with, as well as the last thing it was computed, well, it's going to connect the two, right? Connect, I to I plus 1, and then we're going to pass on I for next iteration, which is going to have, I minus 1 connected to I, right? This might be one of the few times or the only time you see semicolon in this course, right? If you have a semicolon in your function literal, I think 1 in some extreme cases is okay, but 2 is probably a sign you should not be using a function literal. But the reason why we're doing this, of course, is this connection doesn't return anything. It's just performing a side effect. And thus we need a second line to actually indicate the thing we're trying to pass on, right? So remember, it's kind of the syntax of these function literals within a fold right is the current element and the thing that was being passed on. If we're doing fold left, the order of these two things is swapped because they thought that made sense when they designed Scala. But yeah, this is a little bit of a kind of a hairy use of functional programming because we're basically using fold right, not so much to aggregate, but to iterate, right? And we're also counting on a side effect, which normally, as I kind of said, you should use something like for each for a side effect. So why not use for each here? Well, we need to use for each with like a var or something, right? And so Here we actually didn't use a var. The mutation is simply just kind of swept under the rug by, passing along this parameter with our, functional programming. Now, so far, perhaps I may have convinced you that these folds kind of perform functionality that this for loop does. So the question is, what about the rest of the logic here? Well, let's kind of talk our way through that. In terms of the conditions when this whole thing is triggered, well, it's triggered when we are shifting or the NQ is firing. And so what is going to happen? Well, let's go through cases one by one. If we're doing a regular NQ, well, it makes sense. We'll, pull in the bits from there. And so remember, this is going to be kind of the default value passed in. So the highest entry is going to be connected to this, right? So we're going to take it in from the bits. So that's kind of what we want already. We wanted, entries that last to kind of be io.nq.bits. So that is what we wanted, right? When we're firing. Okay, so that makes sense. But now what about the case when we're shifting down? Well, when we're shifting down, we don't touch that. But as we said a second ago, if we're shifting down and we're not NQing, we actually don't really care about the status of those bits because we don't care, right? Those bits only matter if that entry is marked as full, right? If it's empty, we don't care. So actually, we are going to be pulling bits into the register, but we don't care what they are. And the reason why is look at the full empty bits. Well, with these full bits, right, we're going to do the same kind of, passing down functionality, but then we're going to set it to, are we NQing, right? So if we're not NQing, we're going to be putting a 0 into there, right, which makes sense. If we're shifting down without NQing, we want a 0 in that first entry. And if we are NQing, well, then we're going to be, .fire is going to be true, and then we are going to put it in there, right? So you can kind of see how, this is a very compact use of functional programming. We're kind of cheating by using full to do iteration, counting on a side effect, passing things around, also very carefully using the initial thing kind of passed into this full to kind of handle this. So if this all sounds complicated, you're not alone. I include this as an example of functional programming. I think it also kind of shows the conciseness and the power possible. I think in this case, it's less readable, right? So readability is a major concern. So I will argue against it in this case. Let's not use it. We can get what we need accomplished, perhaps, maybe a little more verbosely, but I think someone can kind of read this and have a better sense of what's going on. Cool. Let's go ahead and, run this. And we can, simulate it. Sure, it does the queuing behavior. Now we can let it have multiple entries. That works. Let's talk about one of the big shortcomings about this issue of bubbles, right? So the issue is, if I NQ and then I DQ so everything shifts down, but then I do that a few times and there's some, bubbles being pulled in here by those DQs, and then I NQ again, we're gonna have maybe a valid entry, a full entry, a bunch of empty entries, and maybe a full entry or whatever. And so it's quite possible you have a mix of full and empty bits here, right? And so these bubbles are going to be problematic, right? Because initially it's going to look like there's nothing to DQ, and then we got to kind of keep shifting down to get that bubble squished out, and then all of a sudden there will be something to DQ. So depending on who's on the other end, if they properly respected the coupled interface to recognize, okay, it's not ready, this thing's going to keep shuffling, it's going to work out. Independent of this bubble issue, let's say I have a 8 entry queue, and I NQ an element, it's actually not going to be visible in the output until 8 cycles later, right? So this fixed connectivity is kind of be problematic, where it's kind of just, steady long path. So our queue is going to work. We're not going to tell somebody to DQ unless it's full, but it's going to be slow, right? We're going to NQ and we have to wait, num entry cycles minimum, right? That's assuming we're, DQing and shifting down. If we're not DQing, you might have to wait longer. And so, you're kind of taking score on what we're doing. Latency is a problem, right? But in terms of what we accomplished, well, we still have the queuing behavior, and we have parameterized data from before with uints. We have a parameterized number of entries. That was the main goal, right? We used to have only one entry. Now we have a parameterized number of entries. Okay, check, got that done. But yeah, we're having a bad time with this latency, right? So number one, even in the good case, it's slow. But also, like I said, if you look at the corner cases where if you have bubbles kind of midway, there might even be a bug in there. Okay, so how can we do better? Well, let's get rid of the bubbles. right? So part of what made the bubbles so problematic was there's a mix of, full and empty bits kind of arbitrarily scattered. And rather than always so we're going to kind of fix that in two ways, right? So rather than always arbitrarily NQing at the end, why don't we NQ at the first available slot, right? So that way, we're basically going to fill from the back to the front, so to speak. The place where we're DQing to the place we're NQing. And so that way, if there are any empty slots, they'll always be starting from here and contiguously down this way, right? And so by defragmenting our bubbles, that'll be good. But also, if our queue is empty, we're going to put it right here, so that way next cycle can be DQ'd immediately, right? So by using a priority encoder, we can go ahead and do a much better job at using our resources, right? Where rather than always putting the same place, independent of queue occupancy, instead we're always going to fill it into the first available slot. So if we're trying to find the first available slot, this priority encoder is going to help us, right? Because by looking at the status of every entry with these full empty bits, it's going to recognize, okay, what is the lowest index that has what I need, right? That's empty. And so now the priority encoder kind of in our indexing choice makes sense, right? Where the priority encoder by default in the chisel library prioritizes lower indices, right? So it tries to find the lowest one, and now we can find the lowest index to be closest to the DQ, right? So yeah, if our queue is empty, we're going to go ahead and put that right away in the last slot, so I always DQ'd right away. If it's really close to full, we NQ over here, right? But the result is if there's any empty slots, they're going to be contiguous and over here. So cool, this priority encoder is going to help us quite a bit. Let's go ahead and see this. And maybe take a second to kind of appreciate how we did our process, right? We started off with a simple one entry queue. We tried to go to multiple entries. Our first attempt at that had multiple entries, but wasn't great in some ways. And here we are now trying to make that better, right? And so it's kind of constant steps where you make one change, maybe make something a little bit of a regression, maybe a little bit not as good, but we're going to kind of keep incrementally working our way up, right? So if we tried to, for example, build this design from scratch the first time, this might have been very daunting. But after having already built a single entry queue and kind of wrapped our heads around, we need to have a bit to track if we're full or empty and how we kind of do the protocol signaling on that, and then moving on to a multi-entry queue and shifting. Okay, and now here we are using a priority encoder to make sure we're inserting in an intelligent place. Okay, so we're going to go ahead and have that priority encoder. Let's talk about this then. Okay, so for the priority encoder, it's down here. We'll come back in a second. For now, let's go back to our entries, right? So we have, the queue entries, the full bits, and actually we're going to want the negation of these. We're going to want to know not who's full, so 1 being full, 0 being empty. We're going to want the invert. We want to call these maybe the empty bits. These empty bits are going to be 1 if empty and 0 if full. So here's a, slam dunk for functional programming, right? We can just say, hey, let's take that vec and just negate every element. Cool, easy. One-liner, right? This is that placeholder syntax. That's cool. And so now when it comes to thing questions like, do we have room? Well, if we have room, that would be saying, is there any entry that's empty? Well, if we do an OR reduction, which in this case we're doing it via functional programming for reduce, if we have any empty slots, yeah, we have room. So that means we're ready. If you want to do a little Boolean algebra and do De Morgan's law, you can say, here we're saying, do I have any empties, right? So I'm doing an OR reduction on the empty list. Alternatively, you could do De Morgan's and say, am I not all full, right? So you could take the full bits and do an AND reduction and then negate that, right? This is De Morgan's law. Cool, okay, and then of course, do I have anything to DQ? Well, because we're using the priority encoder to kind of fill from the DQ point onwards, it's actually only one place we need to check. Is there anything at that place that's ready to DQ? And then we're always DQing from the same location. Okay, and then how we actually do functionality? Well, for DQing, this is our shifting code from before, and we're of course going to mark, and because we're shifting down, we're going to go ahead and mark yet another entry as available, as empty. Okay, and now when it comes to the NQing, this is actually a place where we use the priority encoder, right? So here we're going to use the priority encoder, and we're we're going to ask for it. What is the lowest index of an empty slot, right? So this is taking in, num entries bits in the vec, right? It's going to find the lowest index. And with that index, we're going to go ahead and have that be the place where we both write the data we're enqueuing as well as marking it as full. So there's a few things to kind of point out about this use of the priority encoder here, right? So a question from the chat was, oh wait, is that priority encoder one hot? Not quite, right? So the bit pattern here can be arbitrary, right? The whole point of priority encoder is to find the lowest bit. And so yeah, at this point, it's not one hot because it can be arbitrary. And we're trying to find the lowest bit that's one. Now for the output, it's not one hot. So, if we have num entries bits coming in here, this is going to be the log base 2 of num entries bits and a densely encoded number here. There is inside the Chisel library a other priority encoder called priority encoder 1H or OH for one hot. This one doesn't change the semantics of the input. It's still going to be some number of bits and they could be arbitrary bit patterns. It changes the way the output's encoded. Where here, with the one hot version, you're going to have, n bits coming in, n bits coming out, and yeah, the n bit output will have exactly one hot. However, in this vanilla version, right, we are actually getting an encoded, numerical index, and that's what we're going to be using. Another thing you might wonder is, well, wait a second. Here I have what appears to be like a hardware instantiation inside of a when statement. Does that mean the hardware is conditionally instantiated? So the way to think of this is that, hardware can't be existing, created, or destroyed once it's running, right? It's hardware, it's been manufactured. So this priority encoder is going to be instantiated. What the when statement is going to do, behind the scenes with the Chisel Fertile tool flow is just change with muxes when it's connected to, right? So really, what you think about is your entire module body, you're going to instantiate some number of things, right? You're going to instantiate things outside of when blocks, you're going to instantiate things in when blocks. All those things are going to exist. When you connect things, so really, like I said, when you think about Chisel, at the end of the day, it's just instantiating and connecting. So when you connect things, if you connect things outside of one block, well, it's always connected, right? That connection is just made, it's done, it's there. When you have a one block, it's basically just saying, make the connections inside this one block when the condition is true, right? So rather than connecting, full bits dot last, you may even think of this under the hood as perhaps something like, full bits dot last is connected to basically actually a mux, right? And if this condition is true, right, the thing that the when statement is predicated on, well, then I'll go ahead and do what it tells me to. Remember, mux is true dot false for the comment. Otherwise, I'm going to leave it alone basically for basically what the prior version was, right? In other words, don't change it, right? So that's what we're doing. You probably shouldn't notice it's probably going to be a combinational loop, but that semantically or conceptually is kind of what's going on. Another question might be, oh, well, here I used a, reg of vec. Can I talk about that a little bit? Yeah, let's talk about that. So just a couple slides ago, I was, all boisterous and happy about using a Scala collection to seek because, hey, that was, what we needed. We needed a collection of registers, but we didn't need to dynamically address them in the hardware. Now I'm using a vec, right? In particular, because of the way I need to declare things, it's a reg of vec, but yeah, it's a vec of registers, right? So why did I do that? Well, we actually do need the ability to dynamically address in hardware. If we look at the topology, we can see that, we actually are going to be choosing where we write, and definitely we can potentially be writing to any one of these. And that's why, if we right here we're actually performing a write. The hardware this generator is going to have, basically a selection capability to, take this index and only impact that selected register. If you can contrast this from the V1 design, right, these connections were all static. So we did not need that dynamic selection capability like for vec provided. So that's why we used a reg of vec. Now, a follow-on question will be, oh, well, reg of vec, could we have perhaps just used a mem? Isn't reg of vec and mem pretty similar? Yes. Yes, we could have. In this case, I did reg of vec. In some later designs, I'll change that to mem. But yeah, those two are often quite similar. And, for me, veteran chisel designers, part of why they don't seem so irked by reg of vec, because in my head, it's kind of vec of reg, but that's not allowable declaration-wise, is because they usually just use mem, right? So yeah, maybe mem will be better style, and we'll definitely use it later today. Cool, to check my chat for any other questions. This generated a lot of questions in the live lecture. Cool. So let's see how our V2 is doing. We went through all this work, and we can go ahead and test it. All right, it NQs, okay. So it worked, right? So let's kind of take the score real quick. Implementing the queuing behavior, check. We have a parameterized data width, you went sims before, check. Parameterized number of entries, check. Some real big wins, right? Our latency now is based on occupancy, right? So if our queue is full, yeah, it's gonna take time for your entry to get through the queue. If our queue is empty, it goes in one cycle and can go out in the next cycle, right? That wasn't the case with our first shift register attempt, right? So in that sense, we're doing pretty good, right? From the cycle level functional behavior, we're doing pretty good. So what's missing? Well, we actually can't do the simultaneous NQ and DQ the way this is written. And so that's going to be something to concern us a little bit. And the reason why is, even though these registers are all being written this way, this change, right? Full bits is a register, right? Or register of a vec, right? But it's a register, right? And so this update is not going to be visible until the next cycle. And so thus, when we're trying to use the priority encoder to identify a place to write to, or even in fact it should be firing, we no longer do that, right? We only mark ourselves as ready if we have an empty slot, right? And the reason why is because the way we wrote this code to make it simpler, we didn't handle this case of simultaneous NQ and DQ. So we lost that pipe functionality. Okay, so we lost that. So that's functionally something we would like to get back. In terms of efficiency, now we're going to kind of consider that a little bit. It's not great, right? There's two major problems, right? Number one, it's going to be power inefficient. It's going to have a lot of bit sloshing, and it might have a long critical path. So let's kind of consider both of those. So for the bits, well, if you think about it, within hardware design, and whereas how is power consumed? Well, there's some amount of power that's kind of always consumed when your device is on. That's the static power. Then there's the dynamic power, which is, power very much proportional to you doing activity. And that's usually proportional to how much you're kind of charging and discharging bits, in particular when you're charging, right? You go from 1 to 0 where you're tossing away energy, but when you go from 0 to 1, you're going to need energy to charge it up, right? And so when you think about how as a designer, how to kind of save power, having less hardware is the best way, right? The next best way is to reduce your activity factor, right? And so if you think about the shift register, by kind of copying data down, when we shift, we're writing, all n registers, right? So it's potentially a lot of bits toggling, right? That might not be good for power. And the other dimension was clock rate or critical path. Well, we might have a critical path with this priority encoder, right? This priority encoder is going to be made so big, maybe for 8 entries, this is fine. But if we want to have a 500 entry queue, that might not be good, right? So let's see if we can go fix these issues, right? So we want to get our Putman functionality back. We also want to maybe get a little more power efficiency and fix this critical path. Well, to do this, we're actually going to need a more fundamental microarchitectural change to our design, right? It's not going to be a simple little tweak, not just add another encoder. But that's okay, because we've already kind of learned a lot from what we've done so far, built a lot of infrastructure. Even though we're going to radically change the microarchitecture, it's still going to be okay. It's still going to be an incremental kind of step. So what change am I proposing? Well, the goal will be to keep the data in place. So rather than kind of shuffling things down the shift register, rather than moving the data, we're just going to move where we insert and remove, right? Or NQ and DQ. And this isn't a huge change in some ways, right? We think about it. The original shift register, NQ statically one place and DQ statically another place. Then when we improved it for our V2 design, we used our priority encoder to dynamically choose where we're NQing, but we still DQ statically from one place. So static DQ location, dynamic NQ location. And now we're taking that one step further and also going to have a dynamic DQ location, right? And by doing that, we can keep data at rest, right? We're going to put it into one entry, and it's going to stay there until it's removed. So how does that work? Well, we use something called a circular buffer. And this is a general computer science concept, used also in systems. An idea is, you have some amount of memory or registers, whatever, and you use 2 pointers, right? And you insert a 1 pointer and you remove another pointer. And so here I'm saying the word pointer like in software, but you can imagine in hardware within a mem, this could just be an index, right? It's kind of tracking where it is, right? But the idea is, yes, if I want to insert new data, so you can see in this particular case, someone inserted 1, 2, and 3, 4 in order. And so the next insertion is going to go here. And when they want to DQ, they simply read an entry and then, of course, increment this pointer, right? And one of the reasons this keep in mind is it's called a circular buffer, meaning that when you get to the end, you wrap around. So, if we eventually get here, the next location is going to be over here. This is kind of a classic systems thing. It works really well and can do good stuff for us in hardware. There's one little caveat and wrinkle we're going to kind of separate in a few different versions, right? And that is, how do I know if I'm empty or full? If these two pointers are different, then sure, I insert here and remove from here. Okay, fine. But if they are the same, does that mean that every entry is full, or are they all empty, right? A little harder to know, right? And so, our goal for this iterative agile design process is to kind of get things working and then improve and optimize later. So let's go ahead and say, take the easy way out. The easy way out is going to be that we're going to say, if the pointers are equal, that means we're empty. And how do they differentiate from the case when we're full? Well, we're going to say we're full when n plus 1 equals out. So in other words, if n was here, so n plus 1 would equal out, that would mean we're full. So what does that mean? That means basically that, we're going to be full actually when we're only using n minus 1 over entries. We're actually going to kind of leave one entry always empty. But you know what? For now, to get this new thing off the ground, that's an okay compromise, right? We're said our goal is to kind of, pick the feature functionality we're trying to get and perhaps find ways to make it simpler to actually make it approachable. And so we're going to try this circular buffer approach. And you know what? We're going to waste one entry at first because we want to make this thing simple to actually build. So let's see it. And, oh, wait, actually, this code isn't too long. Let's kind of talk our way through it. So for the entries, we're going to use, a reg of vec. I'm even reminding you here, yes, this could be a mem. For our two pointers, we're going to simply just use registers to kind of hold indices. And well, because we have num entries things and they need to point within there, we can use our log2 trip to find out how big it should be. Okay, so we have kind of our NQ index and DQ index. Initially, they're both 0. And so remember, if they're both equal, that means we're empty. And guess what? We can simply encode that, right? We are empty if they are equal. And as we said a second ago, we are full if, n plus 1 equals out. Right? And so some of our logic actually kind of falls out pretty clearly, right? Okay, do I have room to NQ? Well, if I'm not full, then yeah, I must have room. If, am I ready to DQ anything? Well, if I'm not empty. Cool. And then where do I DQ from? Where do I get the data to DQ? I get that from wherever my, DQ index is, wherever my out is. Cool. And then what does it take to DQ? Well, it's as simple as just advancing that out pointer, right? Right? Because we actually don't bother, zeroing out any elements. There's no other metadata. Because, yeah, if I move the out pointer over, this is no longer in the range of, elements in the queue. Another way of thinking of this queue is that from n minus 1 backwards are all of the current contents, right? And so if you move out over, that cell is no longer part of the current contents. It's garbage can be overridden. Cool. And then what about enqueuing? Well, we only want to write to something if we're enqueuing. Of course, we can use that index to know where to enqueue, and we advance the index, right? And because these are, registers, these updates aren't visible to the next cycle. So, we use it one cycle and then kind of get that plus behavior the next cycle. Now, one thing to note is I didn't do any math here for the wrapping around, right? We set a circular buffer, at the end, we wrap around. Wait, I don't see any of that here. It's important to realize, once again, to make things simple enough to get working, we made this restriction. We said, hey, you know what? What if I restrict myself to a power of 2 number of entries? If I have a power of 2 number of entries, this index is going to be an even, the log 2 is going to be a nice whole number. And so actually it's going to naturally up around, right? Let's say I have 8 entries, right? So log 2 of that's going to be 3. So yeah, the valid indices are 0 through 7, 0, 1, 2, 3, 4, 5, 6, 7. when I add 1 on the 7, it, overflows and wraps around to 0. So I don't need to do any special comparison or modulo to make the wraparound behavior happen if my number of entries is a power of 2. So this is a simplification we're doing right now. And to make it extra clear, we're also using this particular form of addition that's going to not increase the result size. It's actually the default behavior, but to be extra clear, I just put that particular symbol in to be clear today. And so if you remember from our lecture from a few lectures ago, we talked about when building our counter, oh wait, can we be clever and recognize, the thing we're counting to is a power 2 and perhaps not have a comparator for finding that max value and just use a natural wrapping around. But if it wasn't a power 2, we kind of do this optimization. We, did it manually ourselves, and we observed how the chisel standard library counter automatically kind of considered both possibilities, right? Well, for now, we're going to keep ourselves simple and, get some functionality improvement, like using this memory and keeping data at rest, but also put some constraints on there, right? We were willing to sacrifice an entry, in order to detect this empty versus full problem. And we also are willing to constrain ourselves to a power 2 number of entries because that's going to make it easier for us to kind of get going. But yeah, so on the whole, this thing is actually, if anything, looking a little simpler, right? This the Scala code, right? Okay, we can go ahead and define it, and let's go run it. And yeah, if we go ahead and simulate this, it's going to do the right thing. So how are we doing? Queuing behavior, parameterized data width, number of entries, yeah. Latency still based on occupancy. The reason why we did all this is efficiency, right? Data is in place, right? We write it into her once. Most transactions are just going to kind of change the pointers into those indices, which are perhaps, much smaller than log-based 2 number of bits. The actual queue entries are going to stay at rest, right? So that's going to be very good from a data moving point of view. Where do we lose ground? Well, a few places, right? For capacity, we lose one entry to detect this empty versus full scenario, and our capacity must be a power of 2 to the kind of 2 constraints. Additionally, performance-wise, we kind of lost our simultaneous NQ DQ. We would love to get that back. We lost that, in V2, and we still haven't got it back yet. We want to get that back. Okay, so let's see what we can do. So first, let's try and get that last entry back, right? We kind of had distinguished between empty versus full. How can we tell that apart? Well, like I said, if you see the pointers are the same place, there's 2 cases, right? Either just things are wrapped all the way around, or it's, collapsed, right? So if you're trying to differentiate 2 things, we need to remember 1 bit of state to kind of remember those 2 possible outcomes. So we're going to go ahead and add this bit called maybe full. And here's how it's going to work. If both indices are equal, we're going to look at maybe full. And if they're both equal and maybe full is true, we're going to say we're full. If both indices are equal and maybe full is false, we're going to say we're empty. And if indices aren't equal, we don't even look at maybe full, but technically that means that we are neither full nor empty. So we both have things to DQ and we have room. Okay. So then let's go and see how this plays out, right? So a lot of this is going to be the same. We're adding the single bit for maybe full. And so where does this come in? Well, now we are empty if our indices are equal and we're not maybe full, and we are, full if our indices are equal and we are maybe full. A lot of this other stuff doesn't change too much. We can kind of reuse this code and it's still full and empty from before. We're still doing the DQ. Really much of the addition is really just about this maybe full. We had to kind of add it in here. We used it here. And now we also need to kind of update maybe full. So let's kind of talk about how or when we update maybe full. We update maybe full in a few places. Now if we're DQing, and our NQ index is not equal our DQ index, then we want to unset maybe full, right? So in a situation where we were full and these 2 were equal, now they're potentially going to become not equal. We want to unset it. However, in the process of NQing, in particular, notice how we're going to, when we are NQing and, the new value is going to equal the out index, then we should mark ourselves as maybe full. Okay. And otherwise it's the same. We can go ahead and run this. And cool. Okay. It's working, at least in that tiny demo so far. So, so what do we do? Well, the big thing we did is we now have a can now use all of our parameterized entries, all of our entries, right? We don't have that single empty entry, which at first may seem small, but if you have a 4-entry queue and these are 500-bit entries, yeah, if you only could use 3 out of 4, that would have been a lot of wasted bits, right? And now we don't waste any of those bits. We still have to have a power 2 capacity, and we can't simultaneously NQ and DQ. Shucks. Okay, let's see if we can do that one, right? So how can we do simultaneous NQ and DQ? Well, really we're just going to say we're able to NQ if we're DQing. It's that simple, right? So before, if we go back, we just said, hey, I can only NQ, i.e. my NQ ports are only ready if I'm not full. If I'm full, sorry. Now we're going to say, you know what? If I'm not full, sure, I can NQ. But even if I am full, so implicitly this is false by Boolean algebra if I go over here, and this is going to evaluate it. If I'm DQing, it's okay, right? And actually the rest of the code is unchanged. So why was this why was this not done? Well, we connected our NQ.ready to DQ.ready, right? And so there's now a path here, right? And so just like in the Chisel Standard Library module, the reason why pipe is an optional parameter is that connection may cause a combinational loop in how you use this queue in your design. And so for that reason, you may not want that connection. You may want the NQ and DQ to be completely decoupled combinationally. In this case, they're now coupled. They're now joined, right? So NQ and DQing have a combinational path between them. We got the performance gain, but there is a combinational path there potentially. But yes, this is going to work, and sure. So if we look at what we did, we did queuing behavior, and we got our NQing and DQing back in the same cycle back. Nice. And we already had the benefits of our in place things. So what were our shortcomings? Well, capacity still must be a power of 2, and we still have a combinational loop. Well, no, we introduced a combinational loop potentially between IDQ.ready because we connected it to DQ.ready. Shucks. Okay, well, let's take one last stab at this and see if we can't tidy up some of these issues, right? So in particular, we're going to remove the power 2 restriction, and we'll come back how we're going to solve that. We're also going to solve the issue of the possible combination loop by making pipe a parameter, right? So if someone says pipe is true, just like standard library queue, we're going to allow them to do this, and we're going to continue to simultaneous NQ and DQ, but we potentially are inducing this connection, which could be the last link of a combinational loop. If someone wants to avoid that, they can set this to false, and boom, they get that. So a little bit of Scala parameterization and generation, and we solve that problem. Now let's talk about some other places we clean this code up, and we'll come back at the end to how we solve this power 2 problem. So now, like we said before, we could use a mem rather than reg of vec, sure. So we did that. It's a little tidier. If you think about how we're using these indices before, we were kind of re-implementing a counter, right? We actually didn't recognize a common pattern there, right? We're like, oh yeah, it's seeing the point to something, and then we add 1 to it, and then use the wrap around. And we're very worried about wrapping around automatically because of power 2 things. That's a counter, right? Recognize a common pattern, right? And so let's just use a counter. And so yeah, we can replace these indices with counters. Notice I don't have to do +1 anymore. I actually just now say .inc, right? So that looks a lot like a function call. So let's kind of talk about what's going on in the hardware. What's going on in the hardware is this is, yes, a Scala function call, but it's going to basically just be substituting in chisel connections. In particular, it's going to substitute in connections that cause this counter to increase, right? And our counter is going to automatically handle wrapping, right? So our counter is not only going to automatically handle wrapping. You just tell how many things to count from, right? So if you power 2 number of things versus not a power 2 things, we saw from before that counter is going to automatically either, if it's not a power 2, detect the maximum value and force the wrap, or if it is a power 2, it doesn't need to do any comparisons and make the hardware simpler and just count on the bits naturally overflowing and cutting off. So that constraint no longer applies to us, and it was nice is we can just no longer require this power 2, and we're reusing a component, right? So this counter is not only being reused for us, but it's also, in this case, providing extra functionality. Where before we had this constraint where we're worried about the wrapping and the max value, by using a counter and just counting on this pattern it provides of incrementing for us nicely and doing that, and it actually under the hood does optimizations for us, that's fantastic, right? That's great. And And then in terms of other things, we tied up the code a little bit. We did a manual, use of common source expression elimination. And the reason why it comes up in multiple places, right? And so where are we using this? Well, for full and empty, sure. But also, for NQ and DQ, as you saw before, of course, we're going to, increment our counters and change the entries. We also factored out the logic for maybe full, right? And at first, this might seem like a mouthful, but in some ways, I think the insight displayed in this code actually in some ways makes it more clear to understand what's going on, right? So if I'm NQing and DQing in the same cycle, the gap between the in and out pointers is not changing, right? The amount of entries in the queue is not changing, right? If I have 4 elements and I'm NQing and DQing at the same time, I still have 4 elements, right? Even though one came out and one came in, I still have 4 elements. And so this maybe full thing really kind of only matters when there's a difference between NQing and DQing, right? That's the only time it's going to change, right? If whatever value it has currently, which if the indices aren't even equal, don't care, but if the indices are equal and we're simultaneously NQing and DQing or simultaneously doing nothing, that's fine. So really it's only if we have a flow mismatch, right? If we're DQing and we're not NQing or NQing and not DQing, and the indices are equal, then we need to kind of change it, right? So, if we went from n-1 to n, so we're NQing but not DQing, and now the things are equal, then yeah, then we should recognize, oh wait, now we are full. Cool. So yeah, let's go ahead and run this. And it seems to work so far. So, how we're doing? Queuing behavior, parameterized data width, parameterized uint, parameterized number of entries. Can be any number of entries you want. Doesn't need to be a power of 2. No wasted spots. It's efficient. We don't need to worry about bits sloshing around. It's kind of written in there once and then removed. Our logic's a lot shallower, right? We don't have this priority queue that goes deeper and deeper with more entries. When we have more entries now, our memory gets bigger, our pointers get bigger, but it's growing at a log 2 rate rather than a linear rate, so that's way better. We once again restored ability to NQ and DQ in the same cycle. So yeah, it's pretty sweet. What's the shortcoming? Well, we're still doing uints, right? So if you want something more sophisticated in uint, can't do that. So in order to do something other than uint, we're gonna need to template the type we're working on. And guess what? That's my topic for a future lecture. But I want to set this up for today and kind of see what we can do as kind of iterative agile design process. Notice how we went on this road where we start off with wanting to build a queue. This thing is pretty sweet, but knowing all these optimizations, nuances, and designs would be really hard to do the first time, right? And so what we did is this kind of agile incremental approach, right? Start off with a single entry, then went to a shift register, and realized, oh wait, long bubbles. What if we use a priority queue to insert in the right place? And then that was better. And then we went to this memory mode where we kind of have 2 pointers in a circular buffer, right? So we went through 6 versions, kind of incrementally improving it. And yeah, along the way, maybe you add a little functionality, maybe you lose a little functionality, sometimes regressions, but in general, it got better, right? Otherwise, you won't make those steps. Even so, you maybe take a trade-off, look at make this thing better at the cost of something else, but we made progress, right? So one question from the chat I'll address briefly is, what about expectations for the final project? So yes, in the final project, I really, really am going to encourage you to take this kind of agile iterative approach where you're going to get something going, close the loop minimally, and then kind of keep adding and building onto it. Definitely. It's going to be part of the project. And we'll be talking about the project in more detail in tomorrow's and Friday's lecture. Have a good day, folks.